And, whoa, what is that? Oh. You okay? Maddie, go ahead. The first three questions?
Yes, it's number 1, 2, and 3.
Okay.
Because number 1, C or B, I don't think you learned about Lewis' definitions of acids and bases, right?
Was it question?
1B.
Oh, so guys, here's the deal. Looking at 1B. So Lewis, do this with me quickly. So Lewis, acids and bases. You understand Lewis dot structures. Lewis thought about electrons. Kate, you're going to want to put your phone down and focus with me. So guys, it goes like this. Watching my hands, Bronsted-Lowry. What do acids do to protons? Come on, y'all. Bronsted-Lowry, what do acids do to protons? Gives them away. What do bases do to protons? Takes them in. So guys, think about it this way. Bronsted-Lowry, protons. Protons are positive. So if you're going to define an acid and base by protons, acids give them away, bases take them in, yes? But what's going to happen to the logic if we switch to electrons? It switches. So protons are positive, electrons are negative. So if the electrons are negative, the direction changes. So now let's do it again. Bronsted-Lowry gives away acids give away positives. Guess what they do with electrons? Take them in. Okay? And then guys, bases, they take in positives. So guess what they do with negatives? Give them away. So it's the opposite logic. We're going to leave that for now. But the idea is that if you can remember that electrons are the opposite of protons, then the electron direction is opposite the direction Bronsted-Lowry for protons. So.
And then
2C. Okay, so let's, and I need to tell you right now, my board is struggling mightily. No, about the same. That's a little worse. Case in point. Okay, so guys, let's take a look at 2C. So looking at 2C together, this is going to be a super big idea in chapter 17, but let's talk about it right now. So guys, in 2C, we've got this. We've got HX, and that is reacting with Y minus, and this is in equilibrium with HY and X minus. So guys, let's have a bigger conversation. Ready? So HX, is it an acid or is it a base? How do you know it's an acid? Because it gives away a hydrogen. How do we know that it gives away a hydrogen? Because we've got what's left when it gives away a hydrogen. Classic conjugate base. This is our acid. This is our conjugate base. Is that okay? Then guys, do this. This is obviously now our base. It can't be an acid because it doesn't have any protons, but you can verify that it's the base because we've got HY over here, and then that Y negative took in the proton, making Y minus the base. Is that okay? Okay, now look at question C. Guys, this is important. Question C says this. If you mix equal concentrations of HX and NaY, will the equilibrium lie mostly to the right or to the left? And so guys, the idea is this. When we add NaY, that makes the concentration of Y go up. And if the concentration of Y goes up, what does Le Chatelier's principle say it's going to do to the equilibrium? Drive it to the right. So it'll drive to the right. Does that make sense? Is that okay? Is that okay? Okay. All right. That's guys, you're going to find out in chapter 17 that's how we make buffers, but we'll talk when we get there. Yeah. Didn't we? No? Really? So question, you're right, we will today. So yeah, let that be. Sorry, that's weird. No, we'll you could probably sort it out, but we'll talk about it today. Okay. What else, y'all? Other questions about the homework? You guys, yeah. Let me see if I can get out of this mode while we're here. Hey, it worked. I did that? Hold on, let me catch up with you. I need way more context. 46? No, you're good. Oh, this is just the dilution equation. Oh, okay, I'm back. All right, now I'm good. Yep. Okay, so this, give me a letter number here, Kelly. It's 46 what? C? So I think I'm starting to get a head cold and my ears are all plugged up. So this being plugged in, I do it again. 46C. Okay, so it says this. It says you have 10 milliliters of 0.01 molar CaOH2 and you dilute it to 500 milliliters. So your question is, why did we not convert to liters? And let's answer the question this way. So first of all, let's make sure we're clear on the math. So we've got the dilution equation, right? So we know the molarity is this. We know the volume is this. We know the new volume is this, and we want to know the molarity, right? Now imagine that we did convert to liters. So if we converted to liters, we would do that by dividing this by 1,000 and then dividing this by 1,000. And if we did, this would become 0.500. And if we did to this would become 0.010. And guess what? The answer is exactly the same. You shouldn't have. If you and so there's 11 different algebra ways we can talk about this, but if you divide this by 1,000 and if you divide that by 1,000, that change factors out. Or you could think about it this way: the ratio of 10 to 500 is the same as the ratio of 0.01 to 0.5. So however you come at this, it's unnecessary to convert to liters because the ratio remains the same, because to convert to liters, you're applying the same change to both sides. And so as a result, it's not necessary. The fact that you got a different answer was just a calculator thing, probably, because it should be exact. Did anybody convert to liters, or did y'all just do it this way? If you did convert to liters, did you get the same answer? You should have. So try it again, and if it's continuing to not work, we can talk, but it should be exactly the same. And algebraically, we can explain why. What else, y'all? You guys good? We okay? All right. So, guys, and I don't want to rush. I know this is a lot of foundational stuff. Are you really okay? Okay, so guys, you are going to need calculators. You are going to need a place to take notes. You're going to need your AP equation sheets. And we're going to get this recorded. Oh, thank you. Pause. Resume. All right. So, does anybody else need an AP equation sheet? You guys okay? All right. So, guys, calculators at hand. Some of you that were paying attention know where this is headed today. But, guys, what we're going to do to get started is we're going to make an important tie back to something that we said at the end of the last day. And that's going to allow us to move forward. So, guys, today is the 15th. We all survived Valentine's Day, I hope. Did I tell you about the Valentine's Day meme that I saw? No. Did I really not? You should show it. Oh, I'll just tell you about it. So Basically, the meme said this: if you're sad because you don't have a Valentine's on Valentine's Day, realize 2 weeks ago you didn't have a groundhog on Groundhog's Day, and that turned out just fine. I said, I like that. That's okay. All right, so guys, the math is accessible. The concept is important. The math is accessible. The concept is important. Chase, let's get going. Guys, draw yourself a beaker. Next to that beaker, please identify this as a 1 molar hydrochloric acid solution. And then, guys, at that point, please do, let's make it 0.1 molar. And then, guys, at that point, please do 2 things. In the beaker, draw what's in there. And let's include water. Actually, let's do this. Do it twice. We are going to draw a line across our beaker. And above the line, let's include water in what's in the beaker. Below the line, let's not include water in what's in the beaker. And then, guys, off to the side, please calculate the pH. You need your calculators. Once again, guys, above the line, include the water. Below the line, do not include the water. And then calculate the pH, showing your work. Do I even have to say that? No, probably. Let's say it differently. To the level of detail that you're planning on using when you take the AP test. Huh? You guys done? So which one did we do above the line, with or without the water? With the water. Okay, so let's talk. HCl Strong Acid. That strong acid gives away protons. Where do the protons go? To water. What does that form? Hydronium ion. So guys, in this beaker then, we have hydronium ion, and we have chloride ion, and that's it. Now, what if we decide not to include the water? Well then, guys, we've got hydrogen ion and chloride ion. And we could represent this in either way, because we know the water's there, and so we could or could not choose to represent it. But guys, we understand that in reality, there's none of this. There is no free hydrogen ion, no protons, because they grab a hold of water and they form hydronium. Questions there? Now, guys, do this. Oh, please.
So, for calculating pH,
That's exactly where we're headed, Cade. So in a moment, we're going to say this. pH is the negative log of hydronium ion concentration, but we could just as easily put hydrogen ion concentration in there because we understand they're the same. Which one's on the AP sheet? Why do I not even see it? Oh, there it is. They just put hydrogen. Do you see it there? Katie, you okay? Okay. So, guys, do this with me. Oh, please. Uh-huh. Yeah. 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 Totally fine. Absolutely fine. Yeah. So guys, do this with me then. Draw a vertical line this way. and below or above, doesn't matter, write down the molarities of the things that are on either side of that line. What is the molarity of hydrogen or hydronium ion? What is the molarity of chloride ion in this solution? So let's talk. Guys, the molarity of hydrogen or hydronium ion is 0.1 molar. The molarity of chloride is 0.1 molar. Is that okay? Okay, now an important chemical point. Why is that true? Why is this molarity the same as that molarity? What about this acid makes that true? It's strong. Guys, this is setting the stage for what we're about to do. Because if this acid were vinegar, if this acid were vinegar, these would not be the same. So let's make sure we're clear. If we went through and did this again, well, actually, wait, we'll just do it again with vinegar. But guys, let's finish this thought. We now need to figure out the pH. So we go pH is equal to the negative log of 0.1 molar, and that would be 1.0. Yeah? Guys, you okay with that? Thoughts, concerns, questions? You're okay? Okay. So guys, let's actually have the experience of doing this. I was planning on just sort of zipping through it. But I'm realizing that that's probably not going to be appropriate. Well, I mean, let's just do it, if I can. So here and here, I'm standing here like I'm thinking, but in fact I'm just cussing on the inside. So guys, let's do this again. Only now, let's make our acid 0.1 molar. And just to simplify things, let's include the water, but let's only do this once. We're not going to do it with and without the water. Guys, identify what's in the beaker. If this is vinegar. Acetic acid. All right, so what have we got? Well, guys, we know that we're going to have some CH3COOH. How do we know that we're going to have some of that? Because it's a weak acid. It doesn't all break apart. So we're going to have some of that. But guys, for the ones that do break apart, what does that form? Yeah, some acetate ion and some hydronium ion and then water. Right. But guys, you see now that we're playing a different game. When we're dealing with weak acids, we now have this situation going on. But let's be clear about this. Where is this in the beaker? If you grabbed a bottle of acetic, well, you did. You titrated acetic acid in lab the other day. Could you see the acetic acid molecules? No, they are dissolved. They are aqueous, but many of them are not broken apart. Do you see that difference? They are dissolved, they're just not protonated. So now, guys, we need to do this. Don't do this with me, but let's set the stage. So what we need to do now is we need to figure out the pH of this solution. So then the question becomes, what's the molarity of this? Is it 0.1 molar? No, because it's a weak acid and not all of it breaks apart. So will it be more or less than 0.1 molar? Less, because not, and guys, you clear on that? Not all of this breaks apart, so it doesn't all turn into hydronium ion. So the amount is going to be less than 0.1 molar because not all of the acetic acid breaks apart. The question becomes how much less? Because in order for us to figure out the pH, we need to know the molarity of this. So guys, how can we figure out the concentration of a substance that doesn't completely break apart in water? Icebox, and that's where we're headed next. Do you see how this goes? Okay, oh yeah. But guys, there's going to be this moment where you're going to go, math is a little bit cooler than I thought it was. You'll see. We're going to do some mathematical gymnastics, if I can get my board to switch, that actually makes this interesting, at least to me. Go ahead, Kate. You could, but we don't need that to come up with pH. Let's play. All right, so guys, as introduction, we are now, and did you catch this? Sorry, let me go back up. Guys, what we're talking about now are the fundamentals of weak acids and weak bases. So, the idea then is this, that weak acids are most of the acids. There's only 7 strong, everything else is weak. These guys do not completely protonate in water, and instead they reach equilibrium. You guys all okay on that? Probably you don't need to write that down. But guys, what I'm going to ask you to do is this. Consider a hypothetical weak acid, HA. Because what I'm going to ask you to do is write the equation that represents the protonation of that acid. So guys, whether you write down the statement or not, please write down the protonation of HA. What's the question that you should be asking before you get started? Do we include water? The answer is no, don't. Don't include water. You guys all done? So it looks like this. We've got HA, and HA breaks apart, and it forms H+, and it forms A-. But guys, what's my mistake? Double-headed arrow. And this is the expression, the reaction that represents the protonation of acetic, or of a weak acid. Now guys, do this. Write the Kc for it. Down below, write the Kc. So we've got Kc is equal to products, hydrogen ion, and A- conjugate base ion, all divided by HA. Now guys, did any of you have a little hesitancy when you were writing down the denominator of this fraction based upon what we ran into with water? Remember how in water we got rid of the denominator because it was a pure liquid and as a result doesn't show up in the equilibria? Does the HA show up in the equilibria? If you're not sure, this is why I drove this point home as hard as I did. So guys, the idea here is this. This is our acetic acid, right? We talked about this. Is that dissolved in water or is it just sitting there? It's dissolved in water, right? So it is aqueous. It's not protonated, but it is aqueous. So even the weak acid is fully dissolved. Be sure you're clear on that. It is fully dissolved. It's just not fully protonated. And as a result, it does... Guys, I'm sorry I'm struggling so much. As a result, guys, it does show up in the equilibrium expression. Yeah? No? Gave away a proton. So yeah, literally. So Josh's question is, what does protonated mean? And it literally means just give away a proton. So this is the representation of the protonation of this acid. But the trick is this. In the beaker, you're going to have HA dissolved in water, and you're going to have protons, and you're going to have conjugate base ions, all of those in the water. So they're all dissolved, but they are not all protonated. They're the same. Protonate, that's a great question. So protonation is the word that we give to the ionization of acids. But that's a great clarifier. They're exactly the same. I've never heard it if there is. Hydroxidization. No. So guys, are we settled then that this is in fact the Ka or the Kc? You see where I went? This is the Kc, but guys, do this with me. This is the Kc for a weak acid. So take your C and give it a tail and turn it into an A, and now find it on the AP equation sheet. See what I did right there? Huh? I know. You got it? Please, Brisha.
So, weak acids can still be like corrosive and stuff. What part of the acid?
Yeah, so, and the answer is both. So Brisha's question, if you couldn't hear it, is weak acids are still corrosive. So what does that mean to be corrosive? And so when we have acids, we know that universally acids give away protons, whether they do it fully or not fully, they give away protons. And all the protons that they give away become hydronium ion. So if you spill acid on your arm, whether it's weak or strong, a lot of times the thing that's hurting you is actually the hydronium ion. In many instances, stripping apart the cell walls of your cells. But then the thing that's interesting about acids is it can also be the conjugate base. Like hydrofluoric acid is way scarier than it should be, because not only do you have hydronium ion, you also have fluoride, and that stuff's no messing around too. And so sometimes the conjugate base can also be a part of the reactivity of an acid, whether it's strong or weak. But for the most part, it's the hydronium ion. Is that okay? Chase, you good? Yeah. Okay, guys, are we all settled here? Are we good on this idea of Ka? Is that sitting well? Okay. So, guys, this then, pray for me. Come on board. Wait, you guys were praying. It's supposed to be okay. All right. I think I can do this now. All right, so you guys all found the Ka expression, right? This has a name. This is called the acid dissociation constant. But guys, fundamentally, you've got to understand something about Ka. And it goes like this. Ka, and I'll just write it out again. And remember the equation that we're looking at. So guys, looking at the expression for Ka down at the bottom, let's just review. What's the numerator? Is that product or reactant? The products are in the numerator, right? So guys, make this connection. The bigger the value that Ka is, the stronger the weak acid. Does that make sense? The bigger the value of, and this is worth writing down. It's going to come up in the notes in a minute, but let's just do it now. Guys, Ka communicates information to us. The bigger the Ka value, the stronger the weak acid. The bigger the Ka value, the stronger the weak acid. Yeah. But it never gets there, right? But it gets closer to completion. But Cade, you're exactly right. When we say stronger, we mean protonate, breaks apart, gives away protons. And so the bigger the value for Ka, the stronger the weak acid. Does that make sense conceptually? Okay. So guys, the idea then, as we said, is the larger the value of Ka, the stronger the weak acid. Yeah. So I actually was thinking about saying this, and I'm like, it's going to be distracting, and I was going to skip it. But because you brought it up, let's talk about it. So what would happen if we did this for a strong acid? So now all of a sudden, this is a completion arrow. How much of this do we have left? None, making this functionally 0. And if you divide by 0, which we know actually isn't a thing we do, but do you know in math what we say the value is if you divide by 0? It's undefined. So what is the Ka value for a strong acid? Undefined. That's actually, if you were to look it up, and some tables include it, the way they denote strong acids is undefined Ka values. Yeah, it's a great observation. So, guys, are we all sort of gathered around this idea? We're going to icebox now. Now, guys, here's the deal. We're going to do 2, and then we're done for the day. That's all we have left to do today is 2 Ka calculations. But, guys, you seriously, when you get to college and when you start solving not only these, but the problems that you are going to see in Chapter 17, guys, what we're going to do today, and this is going to seem heavy-handed, I am going to very specifically talk you through how we're going to solve these ice boxes. I know that you already know how to do this. But guys, what I'm going to do is I'm going to establish a way of solving these that when we get into chapter 17 is going to make chapter 17 so much easier that when you get to college, you are going to achieve like hero status in the eyes of your classmates. Because university professors have an amazing ability to make these complicated, but the way that I'm going to show you to solve them always works, and it's so much easier that you will be seriously a hero in the eyes of your friends when you show them how to do these. So guys, please, as we're doing this, we're going to do the math and we're going to solve these, but we're also going to do it in a way that sets up chapter 17. Okay, so all I'm asking is go slow and do it like me. Okay? All right. So, guys, with that said, let's go. I seriously want to just... Is it asking too much? I click here. It moves. It knows that it's a pointer. And yet, okay, fixed it. Now can I get rid of the dots? All right. So guys, do not write down the question, but we are going to solve this together, and it says this. A student, that could be you. A student prepares a formic acid solution. If the pH is 2.38, what is the Ka? And then additionally, guys, this is a new idea. What is the percent protonation? Now, guys, we are going to dig into this together, and you've already understood we're going to solve this systematically in a way that's going to make you successful next week. So, guys, do this with me. We're going to do an ice box, but we're always going to set it up this way. Guys, here we go. Leave yourself some space to the left, and then moving about 1/4 of the way into the page, we've got formic. Oops. We've got formic acid. Please write it down. Now I have a question for you. Why did we not put the H's together? Because one of those hydrogens is what we call the acidic hydrogen, which is the one that's being given away. Is that the one on the left or the one in the middle? The one on the left. It will always be first or last. Now this. Guys, draw yourself a yields arrow that's a little longer than you think it should be. You will see why in chapter 17. Then, guys, what you're going to do is you are always good. If you're writing right now, stop. well, if you're writing besides zeros. Guys, we are always now going to do this. Put the conjugate first. We know that this is going to break into protons and conjugate base ions. Always put the conjugate first. So we're going to take off the acidic hydrogen and we're going to get this. What's its charge? Negative because it lost a proton. And then we're going to put hydrogens. Guys, you're going to find out this matters. Never put the protons first. Always put them second. All right. So now, guys, at this point, this is going to feel more iceboxy. So let's icebox. And now, guys, let's look at what we know. Just looking through the problem, we know that this is a 0.1 molar solution in formic acid. So that's obviously the dude on the left. But is that the initial concentration or the equilibrium concentration? It's initial. That's what the student made. So guys, this is 0.10. And technically, well, okay, I'll put molar on it. And then, guys, what else do we know? Are there any other things that we can fill in our table? Zeros where? Over here. Guys, before this reaches equilibrium, we have none of either one of these. Then, guys, anything else? Obviously, I don't ask it rhetorically. There is something else. Cade, what else? I love the way you said that. Can we do something with the pH? And the answer is yes. Guys, pH is related to the concentration of what? Hydrogen ion. At where? Initially or equilibrium? Equilibrium. So we are going to do a secondary calculation that says pH is equal to the negative log of hydrogen ion is equal to the, no, that's not right. Oh, it could be. 2.38 is equal to the negative log of x, or x is equal to 10 to the negative 2.38. There was a time when I had a calculator. Oh, that time is now. So 2.38, make it negative, 10 to the x. 4.2 times 10 to the negative third. You know what I'm going to do? The answer is no. You don't know what I'm going to do. I'm going to write it out as a decimal just because it's a little more visual. So guys, I now know, based upon Cade's observation and the math that he led us to, I now know the molarity of hydrogen ion at equilibrium. So bringing that over, and again, guys, you don't need to write this out, but I'm gonna. Did you all get 0.00417? Okay. Now, guys, do you see the magic? This all starts to fall together. Because if this starts at 0 and goes up to this, what's the change? This. Plus 0.0042. Then this is plus 0.0042. And bless the stoichiometry gods, this balances with all ones. So that's minus 0.0042. So now we know this, 0.0042. And then, guys, 0.1 minus 0.0042 is 0.0958. And now, guys, let's come back to this. What are we solving for? Ka. So in order to solve for Ka, we need a Ka expression. And we're going to go Ka is equal to And guys, I know this is low on the screen, but notice what I did not write down. I didn't write down the generic form for the Ka. You don't need Ka is H times A minus over HA. You can just set up the Ka expression that you particularly need. Then guys, am I getting, well, what I was going to do was I was in the numerator going to put 0.0042 squared. Would that have been okay? Can I say that again? I was going to go 0.0042 squared because this and this is the same, and it's just, but I'm not going to do that, and you'll see why in a minute. So we're going to go 0.0042 times divided by 0.0958, and then we've got 0.0042. Now I'm going to square it just because that's easier. And then divide that by 0.0958. And now I'm going to put it in scientific notation. I get 1.8 times 10 to the negative 1, 2, 3, 4. What do you guys think? I'm actually very impressed with the neatness of my writing. That's some of my best work. Guys, conceptually, mathematically, are you good? We're not done, but are you good with what we did? Yeah. That's a brilliant question. I love where you're headed with that. Santiago said, will the values of the two products always be the same? And the answer is usually. So let's talk. Do you guys understand the question? Implicit in that is a really interesting idea. Implicit in that is that these all balance with all ones, right? So when would this not balance with a 1? And the answer would be if you have a weak acid that can give away 2 hydrogens. We're not going to look at that. But, so Santiago, in chapter 16, yes, these will always be the same. In chapter 17, that will not be the case because we're going to muck around with these equilibria, and you'll see. So in chapter 16, yes, those will be the same. That's a great observation. Guys, anything else? Okay, now let's talk about the last part of this question. And to do that, I'm trying to decide if it's important to keep this all on one screen. I'd like to. So, guys, the last question is this. What is as it says, what percent of the acid is protonated? Guys, this is the equation for this. Write this down with me. It's going to have to be a little small. I really want to keep this on one screen, so forgive me. But I'm going to go percent protonation. Is that okay? Too small? Percent protonation is equal to concentration of H plus.
Evan Campbell is checking out.
Thank you. So guys, this is the equation. The concentration of H plus divided by the concentration of HA. Evan, if you have 2 seconds, you may want to stay for just this bit. If you need to go, that's fine. But guys, let's define some terms. This is at equilibrium, and this is initial. And then it's times 100 to turn it into a percentage. So guys, let's do this together. What is the concentration of hydrogen ion at equilibrium? 0.0042. Forgive me for not putting units, but I'm pushed for space. Now, what is the concentration of of our acid initially? 0.1, and then we're going to do this times 100. So guys, some of you can do the math in your head. Some of you need to push the numbers. I'll push the numbers just to make sure I'm not doing anything weird. Multiply that by 100. And guys, I get 4.2%. Guys, let yourself marinate in that for a minute. What does that mean? Well, guys, look at it with me. Evan, are you going to go? Okay, then I'm going to let you go before I talk about it, because this is important. The screencast is posted, so, well, it will be. See, Evan. So, guys, in order to fully appreciate what this means, come back to the equation. So, let me just talk you through this. This top number, ready? This top number is this number. That represents how much of the acid broke apart. Say that again. This top number represents how much of the acid broke apart. This bottom number is this number. What does that represent? The amount of acid that could have broken apart. So guys, follow the logic. This is how much acid we started with. If this were a strong acid, it all would have broken apart and there'd be none left. This is how much acid could have broken apart. This is how much acid did break apart. Does that make sense? And guys, that ratio for this particular acid is 4.2%. Now make this connection. 4.2% of this acid, let's just call it 4%, easy numbers. 4% did break apart. What about the other 96%? Where is it? Dissolved in water, but not protonated. Josh, do you see what protonated means now? So guys, 96% of this acid is dissolved in water and it's just chilling, not broken apart. 4% of it did break apart, so 4% of it is this and this. So guys, what does this mean relative to being a weak acid? And guys, the answer is this. Do any of you know what formic acid is? It's actually ant spit. This is actually the acid that burns you like there's no tomorrow if you've ever been bitten by a fire ant. So guys, this is a weak acid. But this is an acid that you don't want on your skin, and you definitely don't want it under your skin. So guys, for frame of reference, 4% protonated is actually a pretty scary weak acid. So what does it look like when we're talking about weak acids that aren't that protonated? And guys, those are percent protonations on the order of 0.1 down to like 10 to the negative fifth. Really small numbers. So guys, this percent protonation is actually a remarkably strong weak acid. Does that sit okay? Now make one more connection with me, and then we're going to move on. Guys, what is that value right there? What is that number? Ka. And what did we say that Ka tells us? We said there's information contained in it. What information is contained in Ka? How strong the weak acid is. So now guys, make the connection. We found out, because we know this is ant spit and it hurts, this is a relatively strong weak acid. 4% protonated is pretty strong, and that relates to a Ka value of 10 to the negative fourth. So put all these pieces together. If you see a Ka of about 10 to the negative fourth, that is a relatively strong weak acid, and it's on the order of about 4% protonated, and that's a pretty strong weak acid. Guys, what I'm trying to do is give you a frame of reference to talk about these numbers, because this is about to get interesting. Yeah.
So this might not sound like, this might sound confusing.
No?
If it was like, the number was smaller, does that mean it would be a stronger weak acid?
It would be a weaker weak acid. So if this was 10 to the negative 14th, That would be a significantly stronger weak acid. Because remember, these are negative exponents, right? And so the idea is that the smaller this number is, the smaller this number will be, and the weaker the weak acid.
Yeah.
Is that okay?
Yeah.
You guys good on that? Yeah. We will say it again. Go ahead.
So when the exponent gets smaller,
Yeah.
it gets weaker?
Yeah, so smaller by becoming more negative. So if this were a 6, that looks like a bigger number until we realize it's a negative exponent, and then we understand it's a weaker acid.
Because it's basically saying there's more of the unassociated.
Correct. Mm-hmm. Exactly. So Spencer, putting it all together, what we've said is this. The Ka value tells us the strength of the weak acid. The bigger this number is, the stronger the weak acid is, because that relates to percent protonation, which leads us to talk about how much of it breaks apart, which then leads us to strength. So percent protonation is tied to this, and both of those are reflective of strength. So as these numbers trend together, the higher the Ka value, the higher the percent protonation, and the stronger the weak acid. You guys okay? We are going to run into the bell today, guys. We're just going to let that be okay. We've got one more to solve. And guys, the last one, what did I do last time? Oh,
You insulted it.
that's what in my head, I insulted it. Okay, guys, we're going to solve this seemingly simple question. What is the pH of a 0.3 molar vinegar solution? If you want to write it down, you can, but we're going to solve it together. Guys, what is the pH of a 0.3 molar vinegar solution? Now, guys, first of all, this. Notice the information that you're given. What else are you given? Okay, interpret that number relative to formic acid. Relative to formic acid, is this acid vinegar weaker or stronger? Weaker. It's 10 to the negative fifth. It is about 10 times weaker. So what would you expect its percent protonation to be? 10 times smaller. Are you making those connections? You okay? All right, guys, let's do some math. I'm going to switch to blue. You'll see why in a minute. So here's what we said. CH3, COOH. Then a surprisingly long equilibrium arrow. And then, guys, we need our ions. Hydrogen or acetate first. Acetate, it matters. Now it doesn't, but it will. Good? You guys are going to love this. Watch, this is cool. Here we go. Ice box. So guys, what are we given? Where does the 0.3 molar go? Concentration of this guy, initial. 0.30 molar. What else are we given? Nothing. Everything else is us trying to make sense of this. So guys, let's do this. What is our goal? What are we solving for? pH. But pH is not in the ice box, right? But what can we solve for that we can then turn into pH? Hydrogen ion concentration at equilibrium. So guys, this is our goal. How do we get there? Well, guys, what we know is this. When we make this vinegar solution, some of this is going to break apart. We're going to call that X. And when that breaks apart, we're going to pick up X of this, and we're going to pick up X of this. Now, guys, let's bring this together and let's fill out our bottom row. This is 0.30 minus X. This is X. Hey, that's X. And if we can find x, we can take the negative log of x and we can get the pH. So now, guys, what's our next step? No, not yet. It's coming. What's next? Ka. Ka is equal to acetate protons and acetic acid. Now, guys, we can plug in what we know. Trying to decide if I want to work down or to the right. I'm going to go to the right. So we've got the Ka value, 1.8 times 10 to the negative fifth is equal to x times x times 0.30 minus x. So guys, now we need to solve this for, yeah, Christian. I'm sorry? Sorry, you lost me. Which equation? The bottom? Well, it's 0.3 minus x. No, this is always at equilibrium. Yeah, so these expressions are always at equilibrium. Is that okay? Okay, so guys, what do we have to do to solve this? Bring it all together in quadratic formula? You don't. Guys, check this out. This is super fascinating, but it actually makes a ton of sense. Don't look away. Check this out. So guys, here's the idea. We've got our Ka value, which is 1.8 times 10 to the negative fifth. Put that in context. We found out that formic acid is a weak acid, but it's relatively strong. How much did that break apart? Formic acid, how much did it break apart? 4%. So guys, this is 10 to the negative fifth, 10 times weaker. So how much is vinegar going to break apart? Even less. And so guys, this is the way this works. What does this represent? What does the minus x represent? The amount of vinegar that breaks apart. But guys, what do we know about how much of this vinegar is going to break apart? And here's what we know. We know, based upon the Ka value, that not very much of this vinegar is going to break apart, especially compared to the initial concentration. Guys, we've got 0.3 molar vinegar. So we start with a bucket load of vinegar, and hardly any of it's going to break apart. So guys, this is what we do. We say that we can disregard this. Do it in your math. Guys, get rid of the minus x. Why can we get rid of the minus x? And guys, it used to be on the AP test, you would have to write a sentence that says this: I am disregarding the change in concentration to the weak acid because it's insignificant compared to the initial concentration. I'm not doing questions. What we used to have to say is write a sentence that says, I am disregarding the concentration change for the weak acid because it's insignificant compared to the initial concentration. We don't have to do that anymore. What we have to do is this: put an approximately equal to sign and then rewrite it. Guess what just went away? The quadratic formula. Because now, guys, all you've got to do is take 1.8 times 10 to the negative fifth multiply that by 0.3 and take the square root. And I get 2.3 times 10 to the negative 123 molar. I'm not doing questions. So guys, again, the idea is this, and I know you're frustrated because I'm not taking questions, but you're not at the point yet to answer questions. You still need to understand the process, because we're not done. So guys, again, the idea is this. We set up the Ka expression. From the icebox, we populate it. Then, and this is the important idea, we get rid of the minus x. Stop. Up inside your noodle. Why is it appropriate to get rid of the minus x? Because it's insignificant compared to the initial concentration. Now, how do we know, guys? No questions. How do we know that it's insignificant? Because the Ka value is so stinking small. Ka tells us the strength of the weak acid. And this is even weaker than ant spit. So guys, because the Ka is small, we know this ain't going to break apart very much, and so we can ditch the minus x. At that point, this is gone. To solve it, we just cross multiply and then take the square root, and we get this. But guys, we're not done, right? What's the question say? What's the pH? So now we do an additional calculation, and we come over here and we go pH is equal to the negative log of hydrogen ion is equal to the negative log of 2.3 times 10 to the negative third is equal to, and 2.3 times 10 to the negative third, and we take the log and we change the sign, and I get 2.64. Still not doing questions. Largely because I know what your questions are. So guys, let's do one more thing even though it's not called for. Percent protonation. Just like we calculated it previously up here for the earlier one, let's do percent protonation. So percent protonation is equal concentration of hydrogen divided by concentration of acetic acid, or 2.3 times 10 to the negative third divided by 0.3 times 100. So 2.3 times 10 to the negative third divided by 0.3 times 100. Are you surprised by the fact that it's 0.77%? But doesn't that make sense? That if formic acid had a Ka of 10 to the negative fourth and it was 4% protonated, something that is 10 times weaker, because its Ka is 10 to the negative fifth, will have a percent protonation that is on the order of tenths rather than on the order of whole digits. But guys, functionally what that means is this. 99.3%, using really round numbers, 99.3% of this acid is not protonated. Only 0.77% of it breaks apart. Now guys, this brings us to the critical point. Again, why did we get rid of the X? Why was that appropriate? And the answer is because less than 1% of it breaks apart. And if only 1% of it breaks apart, that's not going to be a very big change. It's a rounding error. And as a result, we can get rid of it because that makes the math easier. You guys good on the idea? What, however, is the one question that we've got to figure out? Yeah. When is this okay? At what point is the weak acid strong enough that we can't do this? At what point does the weak acid, and you guys are going to hate the answer, at what point does the weak acid become strong enough that this is, do you understand? At what point does the weak acid become strong enough that the change is no longer insignificant? Do you understand the question we're chasing? Guys, the answer is this. You're going to hate this. 5%. Why do you hate 5%? Because how do you find out that it's 5% protonated? By doing the math. So fundamentally what that means is what you should do is you should set this whole problem up, solve the icebox using the quadratic formula, and then if the percent protonation was less than 5%, it means you really didn't need to use the quadratic formula. That's stupid, right? So guys, this then becomes the answer. We are not going to tie it to 5%. We are actually going to tie it to Ka values. So it goes like, oh shoot, it's not there. We'll write it in. So guys, the rule is this. If an acid is less than 5%, don't write it down. If an acid is less than 5% protonated, in my head. Now this is going to freak out. Yep. So guys, if the acid is less than 5% protonated, we can skip it. But again, that's not helpful to us because we can't get the percent protonation until we're done solving the problem. So what we do is this. We let 1 times 10 to the negative fourth Ka values. We let 1 times 10 to the negative fourth sort of be our breaking point. If you remember with the formic acid, this was 4.7% protonated. We're pushing 5. So guys, this then becomes the rule. If the Ka value is smaller than 10 to the negative fourth, you are always safe to get rid of the minus x. If the Ka value is greater than 10 to the negative fourth, it's never okay to drop the minus x. If it is 10 to the negative fourth, I suggest you use the quadratic formula just to be safe. But guys, the bottom line is this. I've never seen an AP test where they've split these hairs with you. The Ka values for the weak acids they give you on the AP test have always been less than 10 to the negative fourth, so you can always drop the x, the minus x. Is that okay? Guys, questions? Isaac.
How long, do you have to do the approximate sign more than once, or is it time to just show it at once?
No, you just do it that one time and then you're good. Because really that's all you should have to write out. Because once you've done the approximately I guess in theory maybe you're fine. You're good. You guys good on the ideas? Do you want to take a break? Can we go for like 5 more minutes and then wrap up? Is that okay? Do you guys have it in you? Guys, all we need to do then is this. We just need to pivot. This is going to freak out. We need to bring this then into the conversation. And these are what are called Kb values. So guys, in the same way that we can do Kas, we can do Kbs. But we're not going to solve this, but I want to model it for you because something interesting happens. So in the same way that we can talk about weak acids, we can also talk about weak bases. So guys, the idea then goes like this, and you don't need to write these things down. I'll tell you when to start writing. When we talk about weak bases, guys, we have to include water. Do you understand why? Let me show you an example. Don't write this. Oh, shoot. I'm probably not going to be able to undo that. Okay, it's got to be water. So let me try this. So guys, for example, NH3. NH3 is a weak base. How does NH3 make hydroxide as a weak base? It makes NH4. So when we include the water, then what happens is the NH3 takes a hydrogen and it forms NH4 plus, and then we've got hydroxides. So guys, the important bit then is that weak bases can only be understood as bases in the context of water. Is that okay? Okay, so do this with me then. Guys, let's talk about this generically. So B, let me make sure I do this the way they do it on the AP equation sheet. So let's talk about B, and then we're going to put B in water. Do this with me. We're going to take B, our base, and we're going to put it in water. And when B acts as a base towards water, what's it going to turn into? What do bases do? Take in hydrogens. So this is going to be HB, not an R. This is going to be HB. But what's its charge? Positive, because it took in a proton. And then remaining is hydroxide. Guys, write the Kc expression for this. You guys good? So Kb is equal to products What about the water? Liquid, don't include it. It's this. Find it on the equation sheet. Do y'all see it? You okay? You good on that? Okay. So guys, what I'd like to do then to wrap up the day, is I'd like to solve this with you then. Well, sort of. It says, what is the pH of a 0.15 molar NH3 solution? Guys, just remember 0.15 molar. Actually. So 0.15 molar NH3. So we're going to figure out the pH of this. What I'd like to do is set it up with you, but not solve it. So guys, in order to solve this, just like before, we need an ice box, but watch. Start a little bit further to the left. Do this with me. Why are you starting further to the left? Because you need a little more space. Because this ice box is going to have 4 components to it. Because here, guys, we have to include the water. Then, which are we going to put first? Are we going to put the NH4 or the hydroxide? The NH4, we put the conjugate. Guys, really, technically, it doesn't matter, but it will. So let's just get in the habit. And then this. And then ice. And then, guys, we've got to fill this in. Where does the 0.15 molar go? Top left. The initial concentration of NH3. But now, guys, check this out. What do we do about the water? And the answer is this. Put a squiggle. It does not have a molarity. It's a pure liquid. It's got to be there to make the equation balance because we need that source of hydroxide. But it has no molarity, so put a squiggle. Then, guys, you know the drill. This is 0. This is 0. This is minus x. This is plus x. This is plus x. Then we're going to go 0.15 minus x, and then x, and then x. And then, guys, what do we do next? Go ahead.
So, sorry, how do you know it's minus x and plus x?
Because this is a reactant and it's breaking up. By definition, reactants go down because they're being consumed. So that's being consumed by x. These are being created as products by x. So it'll always be minus on the right and plus, minus on the left and plus on the right. So guys, now we need our Kb expression. So Kb is equal to products on top, NH4 plus and OH minus. And then on the base, on the bottom, it's the concentration of the base, NH3. Now guys, I don't know the Kb for NH3, but I do know this. It is on the order of 10 to the negative fifth. I don't remember. Well, they would give it to you. Technically, if we were solving this, we would have had to gone to the back of the book to look it up. We're not going to do that. But it's on the order of 10 to the negative fifth. Then in the numerator, we have x times x. And in the denominator, we have 0.15 minus x. And now the $10,000 question. Can we get rid of the minus x? Yes. Why? Because the Kb value is less than 10 to the negative fourth. The same rules apply. So we would just go approximately equal to x squared divided by 0.15. And then in order to solve this, we would need to know the actual value for Kb. We're not going to. I know that feels unsatisfying, but we're not. You guys okay? Now, guys, to finish the problem. When we find x, what do we do with it to finish the question? Do you see the problem? Guys, x is not hydrogen ion, it's hydroxide ion concentration. So how do you get around this? Well, you could calculate POH. You could go POH is equal to the negative log of OH. But then, guys, how do you convert that into pH? pH plus POH is equal to 14, and that would be fine. What's the other way to do this? Well, you could go hydrogen times hydroxide is equal to 10 to the negative 14th. 1 times 10 to the negative 14th. That would take you from hydroxide to hydrogen, and then you could go pH is equal to the negative log of hydrogen ion. So guys, there's 2 ways to come at this problem. Either one works. Is that okay? Okay, one last thing to wrap up the day, one last equation to talk about, and we're done. Because guys, this brings up sort of an interesting idea. We've now talked about how do we deal with weak acids, how do we deal with weak bases. But guys, bringing those 2 ideas together brings us to an interesting intersection. And it goes like this. So guys, imagine this. Don't write this down, but watch. So we've got this. Weak or strong acid or base? Weak acid. We've got this, which is a conjugate base. Is it worthless or does it have some strength? It has some strength. So guys, now that we've talked about how to talk about the strengths of these acids and bases, we could look up the Ka for this. But guys, that is a weak base. And we could look up the Kb for this. And here's the thing that's weird. They multiply together to give you Kw. Now understand this. This does not mean that the Ka and the Kb of this multiply together to give you 10 to the negative 14th, Kw. This is an acid. It doesn't have a Kb. So guys, the idea is this. It's the Ka of the acid and the Kb of the conjugate base. The Ka of an acid and the Kb of a conjugate base will multiply together to give you Kw, which is 10 to the negative 14th. Find that on the equation sheet and we're done. You guys okay? Do y'all see it there? It's there still, right? There it is. It's about 2/3 of the way down. Ka times Kb is Kw. You guys good? Okay. So guys, let's talk then about what this means. Imagine if we had a different weak acid. And imagine if this weak acid were stronger. If the weak acid is stronger, what do we know about its conjugate base? It's weaker, and that's going to be important for what we talk about on Thursday. Are we all done? Okay. So guys, take a break. Oh, actually, here, let me give you your homework. This is going to freak out. Just sort of getting used to it. So like this, and here's your homework.